Hi again, everybody. Mr. Kolakowski here. Today I'm going to go through a lesson titled Intro to Wave Speed. This is the second day of the new um, Vibrations and Waves unit. We're in Chapter 16. Let's go ahead and jump right into this thing. Um, Taking a look, this is a pretty crummy picture, but I have a picture of a wave. Now you have to imagine that this is moving. Think of a water wave or something like that. So use your imagination. Imagine that this is propagating to the right. Let's go ahead and define a few things. I noticed some of the notes that you guys submitted are spot on. Some of it is a little bit um, sketchy in terms of details. So let me review some of that right now. If we start wavelength, oops, start with this here. Wavelength, which is symbolized by this Greek letter lambda, is defined as one complete wave is the distance you would say it takes um, for one cycle to occur. Again, you have to sort of imagine that this wave is moving, and you could measure it going from, say, a crest to a crest. You could go, that would be one wavelength if you measured that in meters. You could go from a trough to a trough. That would be one wavelength. You could also go from, say, this point here to this point here. That's one complete cycle, one complete to and fro. Um, so there's a lot of different ways you can measure that off of a wave that's propagating. In this case, this is a transverse wave. The bottom line is measured in meters. In the base metric system, it's the distance from crest to crest or trough to trough, or somewhere else, as long as you're sort of allowing the wave to propagate through one complete cycle. This again is called lambda. It's a Greek letter and represents wavelength. Jumping into the next idea is the concept of as the wave propagates left to right here, the period. And period is, let me write that out over here. Um, the time it takes for one complete cycle to pass. So if you could imagine there's a, a point in space, let's say right here, as the wave is going left to right, and if you had a stopwatch, you could time how long it takes for one complete cycle of the wave to do its thing. This is measured in seconds, and I think what's significant about that is we're going to connect this into wave speed here in just a few moments. Um, to give you the alternative approach of describing the wave movement in terms of time it takes for cycle or cycles it takes for a unit of time, we have this frequency idea. You might remember this from circular motion. This is the number of cycles per second. Number of cycles per second. It's hard to write on this thing really clearly. Okay, and that says second. Um, we use the unit hertz, Hz, hertz, as that's supposed to be an H there, as the unit for cycles per second. And what's kind of interesting about this is that frequency is the inverse of period, and period is the inverse of frequency. Um, so, for example, if it took 2 seconds for this wave to propagate through one complete wavelength, then you could inverse that to find the frequency. That would tell you how many wavelengths or cycles occur per second. Okay, so that's kind of the main idea of some of the base definitions for wave motion. Again, I'm using a transverse wave in this particular case as the starting point. You can do the same thing for a longitudinal wave, but it's a little bit harder to draw. Okay. Now, if we want to kind of finish off this video here, let's look at wave speed. Back in first semester, we noticed that speed. This is the scalar concept. Distance per unit time. If we wanted to convert this into a more appropriate context here for a wave that's propagating Again, you have to imagine it's moving. Okay, the wave is kind of, think water wave, for example, the wave is moving from left to right. What we could do is say, okay, well, the distance that we're measuring here would be a wavelength, maybe a trough to trough or crest to crest. And the time it takes for that wavelength to move would be the period, the number of seconds it takes. I didn't write this out over here, but maybe I should have. It's the time for one complete cycle. Time for one complete cycle. I'm still learning how to write on this thing. It's an awkward angle a little bit. Again, that's measured in seconds. So as you can see, that would also give us the units of meters per second. And if you wanted to be kind of clever about it, you'd say, okay, so that's the speed of the wave. You'd say, well, period and frequency are inverses of one another. So you can rewrite this as frequency times wavelength, which will again give you the units of meters per second. And in fact, if you replace wave speed with this symbol here, v, you get the classic version of this equation, v equals f lambda. Very important equation here in chapter 16. And we can use this for all sorts of situations. It doesn't have to be a transverse wave. It could be a longitudinal wave, in which case the wavelength would be defined as the distance from compression to compression or refraction to refraction. But we'll see if we can focus on that another time. Very quickly then, let's look at a sample problem. This is just something I pulled from a different textbook. There are additional sample problems for you guys, different from this one. It's chapter 16.2 in your book. It's page 425 if you have your hard copy, but you can use your Wiley Plus read, study, and practice link to get to the book. If you go to section 16.2, at the end of this section, you'll see some sample problems using our new friend here, wave speed equals frequency times wavelength, or this version here, same difference, wave speed is wavelength divided by period. Sample number 2 here from a different textbook says, if a water wave oscillates up and down 3 times every second, and the distance between the wave crests is 2 meters, what is its frequency? What is its wavelength? What is its wave speed? Okay. Well, if we sort of look at the details here, this is a water wave. You can hopefully imagine a water wave propagating across a lake or something like that. They give us some details here. The distance between the wave crests. Okay, that's wavelength. They also tell you something important here. They tell you that the water wave oscillates up and down 3 times every second. Okay, what does that mean? Is that period? Is that frequency? Well, let's kind of go into this with the mathematical description. So they're really saying this is 3 cycles per second. So that's 3 per second, okay? I should have just wrote the letter S there, but the word cycle in and of itself isn't really part of the unit. That's just, you could replace that with the word vibration or complete wave length or something like that, but it's really 3 per second. That's kind of what that's saying. 3 waves propagate per second. And if you multiply that by this wavelength here, 2 meters, you can see the units are going to work out for us here. It's going to be 6 meters per second. And that should be the speed of the wave. So I think in the process there, we answered all the questions. What is its frequency, wavelength, and wave speed? If you have any questions, let me know. I hope you guys are doing well. I know this is a really crazy, weird time. I guess I want to apologize to you guys for having to deal with this. We're all sort of dealing with it in our own way, and I hope you guys are doing okay out there. This is a frustrating, stressful time. Do what you can to keep yourself happy and optimistic as best as possible. I'll talk to you guys again really soon. Take care.